told your friend you're not okay. Tell me what's wrong. Felt that way. And guess you're trying to stay strong and fake a smile until I look away. But I've known you too long. It hurts to watch your blue eyes fade to gray as you fade away. As you fade away.
Yeah, I'm about to fade away, cause every time I wake up I feel like it's Monday. Something's going wrong with all the chemicals up in my brain. All of a sudden I don't look at anything the same way. Gotta build up of my thoughts sitting in an ashtray. I'm sorry that I'm so inconvenient, okay. Just let me be me and I'll stay out of your way. I can see the way you look at me, I'm such a disgrace. I never really asked to be brought into this place. You wanna love me? Well then baby have a taste. All the highs and the lows, no you'll never be the same. I don't really wanna.
Interaction of a solar panel and the e-pulse. Will this work? The story started when my father-in-law bought himself 2 solar panels to lower his electric bill by getting some electric tailwind from his balcony. By curiosity, I read the sticker on the back of one of his 400 watt panels, with the question in mind if one of these panels would be good for powering an Infento ride, just as it is, without electronic means. No solar charger, no battery as a buffer, no battery at all. Just a simple cable to connect the panel to the e-pulse. Instant power generated for instant use. The e-pulse can run with up to 42 volts direct current, and without modifications it draws up to 8.5 amps. On the backside sticker of the panel, the values for voltage and current of the panel seem to match with this quite well. Since I wasn't familiar about the performance characteristic of a solar panel, I looked up the panel's data sheet on the internet. A solar panel is not a battery, that's for sure. What will happen if the e-pulse draws more power than what the panel delivers? Could something get damaged? To answer this question, I bought myself this solar panel named GEM 6CS20 from Solar. It has nominally 385 watts. These solar panels have become very affordable. I purchased it in early 2023 for 155 euros, but by the time editing this video in January 2024, the price of this very panel has fallen to unbelievable 60 euros. Yes, you heard right, 60 euros. A full-size solar panel with almost 400 watts that produces power for at least 25 years costs less than a full car tank of gas. Now this panel has a weight of a bit over 20 kilograms, and with 1.6 m by 1.77 m it has a comparable size as the front door of my house, or close to the size of a bed. Panels look quite small when they are mounted on the roof, but inside of the trunk of my family van, this panel looked damn huge. Some panels even have more power, but watch out, they are even wider, like 1.12 m. And this starts to get really exaggerated for an Infento ride. Here I am showing you the datasheet of my very solar panel, but I believe for other panels the general characteristic will be quite similar. I found a few graphs at the very bottom. The very left one indicates the amps over voltage under different sunlight intensities. Let's take the red line as an example, which might be equivalent with best weather and ideal panel orientation in South Germany. I find the graph is a bit confusing because the amps are on the vertical axis. But the amps is what we vary by the e-pulse throttle grip, and the voltage of the panel will be a result of it, so it would rather make sense to display the amps on the horizontal axis. So I will flip the graph around so that the axes are being swapped, and I highlight our relevant curve a bit. Now the reading becomes easy. If we don't touch the throttle grip, the motor draws 0 amps. The voltage will be idling at around 40 volts. If we draw 6 amps, the voltage will drop only marginally to some 38 volts. It starts to get interesting when we come to 9 amps, because here the voltage starts to drop visibly to 35 volts, but this voltage will still make our e-pulse run pretty fast. But in excess of 10.5 amps, the voltage breaks down to 0 volt instantly, so also our motor will get 0 watts of power. I tried this out in the garden with the panel hung to my electric load, and I can confirm that within a span of 200 milliamps, the voltage drops from 35 to 0 volt. For driving this panel, this means we have to keep away from this critical current limit, or our motor will stop running. Unfortunately, this critical current limit changes all the time when the sunlight conditions or the orientation of the panel changes. But the good news is that nothing will get damaged, not the motor and neither the solar panel. To prove if my theoretical considerations were correct, I built up the panel in the garden and hung the e-pulse motor to it. First without a mechanical load. Later I gave the e-pulse some work to do by using the inertia dyno I presented in my second video about e-pulse tuning. At first, the e-pulse controller drew too much current, as it was set to 15.5 amps. This led to an interesting effect. The e-pulse started to oscillate under full load. But what happened here exactly? The explanation is a chain of effects that repeat in a loop. The e-pulse draws more current than the solar panel can deliver. As a result, the voltage of the solar panel breaks down. Now the e-pulse controller shuts off the motor because it has a built-in undervoltage protection that is meant to protect a rechargeable battery against deep discharge. Now the electric circuit is interrupted, and without any load, the voltage of the panel shoots up to 40 volts. Then the e-pulse controller believes that the potential battery is good to go again and energizes the motor by pushing a high current into it. This leads to another breakdown of the panel's voltage, and the circle starts to repeat itself over and over again with a frequency of estimated 5 Hz, which is a kind of tickering. So if you should find your e-pulse oscillates while driving, just twist the throttle grip back a bit. Finally, I limited the current of the controller to 10 amps, and as a result I got this nice power curve. We achieve 190 watts of mechanical output, 46 Nm and 220 RPM final speed. The max power is achieved at only 85 RPM. I kept this in mind and chose a longer ratio in order to get the maximum power onto the road at high speed. The panel itself delivered some 320 watts electrical input, which stays a good bit under the nominal value of 385 watts. If you want to copy this experiment and you don't feel like flashing the controller of the e-pulse, you don't have to. The e-pulse does not necessarily need to be flashed. You will just gain a few watts in the most ideal sunlight conditions, which are very rare in practical life. If you are a technical guy, you may try out to build what I did not. An electronic throttle controller which will let the motor drive just as much power so that the panel's voltage doesn't break down even when the sunlight conditions are changing while driving. The e-pulse throttle will give its analog signal not directly to the e-pulse, but to an Arduino. The Arduino permanently measures the voltage of the solar panel over a voltage divider. Then the Arduino will subsequently try to increase the throttle signal to the e-pulse to just not risk a breakdown of the panel's voltage. The Arduino will give out the calculated analog voltage signal over a digital to analog converter, like the MCP4725 you see displayed. If you should try this out, I would be very grateful for feedback about your experience with this device. Building the Solar Racer. With the electrical concerns all sorted out, I started to build a ride around this panel, or should I better say, underneath the panel. I decided to build this large three-wheeler as it would support the panel in 3 places by vertical posts. At first I tried to build a scissor-like tilting mechanism that would allow to orient the panel towards the sun. Facebook member Michael had the idea to use fast spanners from a bike to make multi-joints adjustable without tools. I also printed this cardan cube to convert 2 U-joints into a cardan joint so the panel could be tilted in any direction. Here in Germany, the maximum solar radiation angle in high summer is hardly above 45 degrees, and therefore it is a fair consideration if a panel that can be oriented towards the sun would be a benefit. If I look at my house roof full of solar panels, a tilted panel would be a true benefit in terms of solar earnings. It is simple physics. The axis of the Earth is tilted by 23 degrees. Germany lays between 47 and 55 degrees latitude and is shown in this model by a red line on the contour of the globe. The best radiation angle for a flat-lying solar panel in full summer and at high noon is 28 degrees, which means that we harvest 12% less energy of what is possible. And a typical 45 degree angle means already a reduction by almost 30%. But anyway, we now want to use a solar panel not on a house, but on a vehicle. Here we have to consider the downsides of a tilted panel. First, a tilted solar panel with almost 2 square meters will be aerodynamically a big disadvantage. It will increase its aerodynamic drag significantly and increase the susceptibility to crosswinds. Secondly, the panel is very heavy with 20 kilograms, and a tilted solar panel will increase the center of gravity. The ride will become prone to tipping when cornering. A third point is the practical use. Would you stop your ride after every change in driving direction to reorient the solar panel towards the sun? Last but not least, the way I built this concept of a tilting panel, it turned out to be totally unstable. Reinforcing everything would have made the ride heavy, but I wanted to keep the ride light and simple. So in the end, the panel got rigid posts. And I even had to reinforce these later on as the panel was starting to swing when driving over bumps. And this swing was fed back over the arms of the kit into the steering. Also, this long frame wasn't stiff enough against twisting, and for safety reasons I fit an adjustable motorbike steering damper I happened to have laying around. In the footage you may have noticed the black arrow front wheels. They have no function, they just look cool. They are made from 5 3D printed plastic parts that are mounted onto the 5 holes on the rims that are meant for the brake discs. Very easy to print. As always, I have uploaded the models for 3 different styles onto Thingiverse, and the link can be found in this video's description. The large black belt sprocket with 63 teeth you may see in a few pictures is not a must. It was good for maximum speed, but the acceleration was really poor and gradients greater than 3% became a problem. Later I fitted the standard 46 tooth sprocket, which was a far better compromise. To support the solar panel I built a T-shaped subframe, and to connect the subframe to the panel I designed this Infento to solar panel bracket that I am also uploading to Thingy. It works for a panel with 35mm of frame thickness, The filament material of my choice are PETG or ABS. Between the ABS brackets and the panel I needed something elastic. I cut some stripes out of a Tupperware, how do you call it? Non-slip rubber grip jar opener? You can find these for a few bucks on Amazon. I am warning you not to use PLA material for the brackets, as it will start to yield in hot sunlight, and you wouldn't want the 20 kg solar panel to fall onto a young driver's head while driving. To connect the solar panel to the e-poles, you need to build yourself an adapter cable. The cable itself should have a minimum section of 1.5 square mm or AWG16, but most solar cables come with 4 square mm. On the side that is going to the solar panel, you will need a pair of standard MC4 connectors. And on the other side that goes into the e-poles, you will need a cable with a molded M12 4-pin connector, straight or angled. AliExpress or eBay are good sources to buy these cables and connectors. The female MC4 connector goes into pin 1 and 2 of the M12 connector. This is the positive line. The male MC4 connector goes into pin 3 and 4 of the M12 connector and represent the negative line. The driving experience. When the ride was finished and the weather was fine, my older sons helped me to carry the solar panel out of the basement. The ride followed shortly thereafter. The panel was fit by profile connectors onto the posts. Finally, I plugged the power lines of the solar panel. Then, my rolling ping pong table was ready to go. Na Pilot, willst du gleich rein? Bereit? Gib mal langsam Gas. Jawohl. Da kannst du mehr Gas geben, dann hört er auf zu zittern. To say it explicitly, building in a rechargeable battery plus a solar charger into this ride would have been an easy and affordable task, as you can see on this slide. The panel would feed its power into a solar charger, like a Victron Smart Solar MPPT 7515 for some 65 euros. The e-poles battery would also be connected to it, and the energy would go in either direction, depending on the driving and solar conditions. The e-poles would be connected to the solar charger like shown, or directly to the second port of the e-poles battery. But I decided not to go along this route with a buffer battery, and I did that for a reason. It is not only that the buffer battery worsens the overall efficiency, no. It is all about the principal question: what matches the sense of a true solar ride? On the internet, I find tons of videos of so-called solar DIY go-karts or boats with spectacular 2000 watt motors driving around like hell even in shady weather. But they hardly deserve the designation of a solar ride. Why? Because these beefy motors are fed to 90% out of a pre-charged battery and only 10% over the solar panel. They could also leave their panels at home and drive just with the battery for their demo videos. They would need 10 times the size of solar area to cover their constant demand of their motors. Or they would need to park their ride 12 to 15 times longer in the sun than the time that their demo ride took. It was my intention to experience nothing but the power that is coming instantly from the sky. Of course, this means that just the shade of a tree, a bridge or a cloud will cut the power to the motor, but this is just part of the experience. The solar industry claims that modern solar panels also generate power on cloudy days. This is 95% a lie and only 5% the truth, because once you drive such a ride, you will experience that only bright sunlight delivers meaningful power. I admit that I always carried an e-pulse battery for emergency cases with me, for not getting stranded somewhere, probably kilometers off from home. But like this, solar and battery performance were clearly separated, what came from the sky and what came out of a power socket at home. The longest tour I did with my daughter was 7 kilometers. And by GPS, we measured a top speed of 23 km per hour. Wherever the solar ride parked, it got very positive reactions. As positive side effect, the kids also mentioned that they liked that the panel was like a roof over their heads and it gave them some shade on the hot sunny days. But finally I had to strip the ride because I found no place to store it. The solar panel is now on my garden house with 7 others, spending the rest of its life with a very useful but probably less exciting job. Without the panel, the ride was of course 25 kilograms lighter, and the kids also used it for a while with a normal battery. Well, that's pretty much it for today. It was great to have you as technically interested audience on board. I hope you enjoyed this video, and if you did, please like, share and subscribe for not missing the next projects that I have in the making. Until then, happy building!